Hi everyone, this is Jay Matthews, and this will be my second attempt at the nuclear fusion presentation. I had my first attempt yesterday, and I got some feedback from some of my friends and colleagues, and I have since made improvements to my slideshow, and hopefully it is a bit more interesting. After watching the thing myself, I actually almost bored myself to tears. Anyway, without further ado, I will begin. My topic is nuclear fusion with an emphasis in magnetic and inertial confinement reactors. My original topic was supposed to be only covering inertial confinement reactors. However, I feel like in order to get a sense of the entire fusion picture, you should be explained what magnetic confinement is as well, because it's actually a very interesting topic. Before I did anything on nuclear fusion for my research, I didn't really know anything about it. So I found this stuff to be actually quite intriguing. Just to give you a basic outline, I'll be covering some basics about hydrogen, a little bit of basic concepts of nuclear forces, and then we'll be getting into the process of fusion itself. We'll get into some applications, and then lastly I'll talk about magnetic and inertial confinement reactors. Please note that everything in italics is for operational definitions. Just gives you kind of a background of what I'll be talking about later on. So the hydrogen atom is atom number 1 on the periodic table. It's estimated that it is a total of 92% of all atoms everywhere. We'll be using it to explain nuclear fusion as it acts as a fuel. But some other interesting things about hydrogen before we move on is that hydrogen bonds are everywhere. In water, it binds water together. It binds our DNA together. Hydrogen bonds are really strong polar covalent bonds that are stronger than most other polar covalent bonds, and that's more of a chemistry thing. I won't really get into it. It's very fascinating. Hydrogen is also used as a model to simplify quantum mechanics, so us physicists can understand quantum mechanics without having to delve into crazy multi-proton systems. So, a brief introduction to two protons, okay? We have fusion, which gets two protons or more, two separate protons in close together, and they will form one single nucleus. But there's a problem, okay? And before I did this presentation, I didn't actually know that this existed, but you have two protons and they're both positively charged, right? So if they're both positively charged, we know that Coulomb's law specifies that two of the same charges will repel each other. So if protons are positively charged and repel each other, how can two of them be bonded together to form a new nucleus? And the answer to that is this nuclear fusion idea. We have a separate set of forces. Instead of the electromagnetic forces and Coulomb's law, we have a new set of forces called nuclear forces, which are about 100 times stronger than electromagnetic forces, but there's a catch. These forces will only act on protons and they will only act on protons at very, very, very small distances. We're talking 2.5 times the diameter of a nucleon. A nucleon just being a proton or a neutron. They're both experimentally, I guess, shown to be the same size. But the area of effect is actually quite small. And you can see, I'm not a graphic designer, but I couldn't find a better photo than this, so I had to actually make this graphic myself. Clearly it's not to scale. This green field right here is the strong nuclear force, whereas these little reds are the protons and the blues are the neutrons. This, of course, is the electromagnetic field, which of course, is not to scale because we know that the electromagnetic field can actually be quite far in acting away from the center of the nucleus. So we get into the process of nuclear fusion. The process is actually quite simple. Two or more atomic nuclei, which in this example we have this 2H, which is deuterium, and 3H, which is tritium. They're both different isotopes of hydrogen. And they come together and collide. And what we have is a resultant helium atom, helium-4, with a little bit of energy in the helium atom, and then we have a free neutron here that has a ton of energy. So the cool thing about fusion, specifically fusion of light atoms, light meaning their mass, not photons and light, is that when this fusion occurs, energy is given off. And let's see. Okay. So why is that? Why is there surplus energy? Well, the thing about deuterium and tritium is that deuterium has a binding energy, which is the binding energy is the energy it takes to pull the protons apart, or just pull the nucleus apart, right? So the binding energy for deuterium is about 2 mega electron volts, and the binding energy for tritium is 8 mega electron volts, which gives us a total of about 10 mega electron volts. The binding energy for helium, however, is 28 mega electron volts. So we have a difference here of 18 mega electron volts, which gets liberated when the fusion happens. So every time we have helium-2 and helium-3 fusing together, we have a liberation of 18 mega electron volts. Fusion isn't an easy thing to do. One does not simply fuse two nuclei. Since I'm nearing the end of my 10 minutes here, I will continue this presentation in part 2. If I can find the stop button. There it is.